In this presentation we are going to look at statistics with R. This is an introduction to R for actuarial students and it corresponds to the CS1B curriculum, which comprises Introduction to R Programming and the Fundamentals of Statistical Analysis. This is an early question in the paper, so it should be one of the straightforward enough questions, question 1 or question 2. Actually, I think this is question 2 to be honest with you. The dataset interest rates contains a series of returns on bonds of maturities 1 year, 5 years, 10 years, 15 years, 20 years and 30 years, i.e. bonds that provide a return on the principal investment after 1, 5, 10, 15, 20 and 30 years respectively. So the exercises ask us to load this up and have this dataset ready. So I have this dataset in the working directory saved as a CSV file, interest_rates.csv. So I read it into my R environment using the command read.csv, and I'm just going to save it as interest rates. Okay. Now, just to check that everything's in order, I'm going to use the head command there just to sort of look at the top of the data set, the top of the data frame. What we have there now is a data frame in the R environment, and just to sort of see the general shape of it, head prints out the first 6 rows, and so there we have our 6 variables, 6 rows, and those are the returns. Okay, so exercise 1. This asks us to calculate the Pearson correlation coefficient for this data. Comment on the correlations between the data using the matrix from exercise 1. So this is essentially bunched up here. So essentially what we can do here is actually just specify the correlation coefficients using the core command. Okay. Now what this does is it generates a matrix of all of the variables. So what we have here is a 6x6 matrix, and this calculates the correlation coefficient for each pair of variables in that data set. For example, the correlation coefficient of x1 and x5 is 0.876. And likewise, you can sort of see it down here as well, that is also the correlation coefficient, just with the order of the variables reversed, but that gives the same value all the same. Likewise, x20, 0.614 when compared to x1, and 0.614 up here. So it's a symmetric matrix essentially. That's by definition what a correlation coefficient matrix would be. Just to specify that this is the Pearson correlation coefficient. You could put in other ones there, but we're not really asked about that, so we'll just sort of take it as read that the Pearson correlation coefficient is the correct thing to do in this case. Now, that answers the question. So essentially, they all seem to be quite positive. Okay, this is the lowest one I can find, 0.4. Remember that the correlation coefficient is a value from -1 to 1, but what we're looking at here is mostly they are above 0.5. Actually, with the exception of this one, they are nearly all above 0.5, which indicates that there's quite a lot of strong positive correlation between each of these variables. It's just this particular case of x1 and x30 that's not so strong, but it's still a positive correlation coefficient. So lots of positive correlations going around there essentially. That's all I can say about it. So the interpretation, the correlation matrix shows that there is a strong positive correlation between returns on bonds of similar maturity. Okay. And it also shows that the correlation between returns is weaker as the length of maturity increases. Let's just sort of go down that row there. X1 to X5, that's actually what we're seeing, alright. Yeah. That it gets progressively smaller. Likewise, if you look from X1 to X10, sorry, X5 to X10, it seems to be decreasing there as well. And likewise over here. We're looking under the diagonal. We're under the 1 value. This is that diagonal here. Okay. Now, I'm just going to sort of sidetrack myself a little bit. Just to remark that there is a visual graphical complement to the correlation matrix that actually makes things really easy to look at. So essentially what we do is we load up this package called ggcoreplot, okay, And what I can do there is apply this command ggcoreplot, which is in ggcoreplot. So this is the name of the R package, this is the name of the command, okay? And I can sort of apply this command to the correlation matrix, okay? So it's the correlation matrix that is made an argument of this command. So this is what I get. Now this is the background of this is an R package called ggplot2. So, by the way, just as a quick remark, that ggcoreplot and ggplot2 are not part of the CS1B syllabus. I'm just sort of adding this in because ultimately this is a fairly easy question. So this actually just sort of increases your knowledge there. So, all around, this is a sort of visual complement of the correlation matrix. So, red is positive correlation, blue is negative correlation. So we don't have any blue there, so it's all red, so it's all positive. And the sort of the strength of the color, how dark it is, how dark red it is how close to 1 it is. And you can sort of see that for most of the interior, most pairs of variables, it is quite strongly correlated. In fact, this is the only time where we sort of see up something quite weak, x30.year and x1 year. Okay, so that's useful to know. So perform a reduction of, this is part 2 of the dimension of the data using principal component analysis with the method of singular value decomposition. Your answer should include a summary of the principal component analysis. Suggest with reasons using the output of the R analysis how many of the components of the transform data should be retained. Okay, so we set up our data frame here and we apply this command prcomp, principal component analysis. Okay, that's what we do. We're going to save that as an object called PCA. I'll just pick that name. And here what we're going to do is look at the summary of that. And so this will transform the data into 6 principal components, sort of 6 artificial variables essentially. And what we want to look at here is the cumulative proportion of how much of the model can be explained by this principal component. So if it's just PC1, that covers 86% of the variance. Okay. If it's PC1 and PC2, it's 97%, 97.754%. That's usually quite good, but actually if we go up one more, PC3 is 99.8%. So if we include PC1, PC2, PC3, those 3 principal components can explain 99.8% of the variance in the data, which is really good. So that's all we need. I would sort of say 3, but actually, you know, it's not wrong to say 2. Just print PC1 and PC2, that just to sort of say that's our upper threshold. Reach 95% is good enough, so just go for PC1 and PC2. I'll go for PC3 here, so PC1, PC2 and PC3, so the first 3. So the R output shows that the proportion of variance explained by the first 2 principal components is approximately 98% and the first 3 is 99%. Therefore, it would be reasonable to reduce the dimensions of the dataset by using the first 2 or 3 principal components. And that's it, I think. Yeah, that's it. Stop it there. Thank you very much.